All right. Okay. So the problem that we're going to do today, or in this lecture, and by the way, in this lecture, everybody from lab 53 and 54 is present, at least in theory. And this morning I met with 54, and yesterday I met with 53. Okay? So we're going to look at a problem that is in chapter 3 of the textbook, and it's a block with a central hole that is being pulled on both sides. Okay. Let me ask you a question. Where do you expect this thing to fail? What is the critical point of this problem? Where do you have to keep your eyes on? Yes. Would you like to give an answer? Yes.
On the smallest cross section?
Where? You're right. You're right.
Where
But
the
where?
diameter of the hole is the diameter of the hole, yeah. At the center.
Okay, but let me ask you this. Let me ask you this. I have a hole here. It has a boundary, right? There is this circle. Where do you expect the biggest stress to be on this circular boundary?
At the top and at the bottom of the circle?
Yes, that is correct. At the top and the bottom. Correct, correct. And this is what we call a stress concentration. Because think about it like this. We have a force, and that force was acting on a big cross-section here. But when it reaches its effect, in the middle, the area has decreased. And if the area is decreased, the stress is going to go up. Because force is constant, area has decreased, the stress is going to go up. And it turns out that the top and the bottom, not the sides, the top and the bottom carry the most tensile stress, and that is what is called stress concentration. That hole or notch is leading to a stress concentration. Okay. Now, if the plate was extremely large, infinite plate, in other words, in the x direction and in the y direction, I have a very big plate with a hole in it. Or the other way around. Think about a plate with extremely tiny hole in it. That stress concentration is 3. Okay, in other words, whatever stress you have, you're acting on the sides of this block, multiplied by 3 is going to appear on the top and the bottom of the hole. In fact, there are tables like this. Now, I don't know whether we do these things in stress analysis anymore, probably not, but I'm pretty sure in machine design, if or design for failure prevention that you took, I think this last winter, you probably did stress concentration. Okay, you can see that when this ratio, this is R over, I think this is, this horizontal axis is the ratio of R probably over some kind of a W, the width, yeah, R over W. If RW is very small, in other words, the hole is really tiny compared to the width of this plate, the stress concentration is 3, right there. Okay, so we're going to model this problem. But there are some issues, subtle issues that we would like to consider. There are different ways of doing it. One is to, well, first of all, the dimensions of the box are given here, and we're going to use that. And the force of 2,000 pounds is the force, not stress point, not pressure. It's the force of 2,000 pounds is applied on both sides of this, on this block. And material properties are given here, etc. So one way is to model the block like this, just the block, exactly what it is, with a hole, and apply forces to it on both sides. The other option is to look at this diagram and see, wait a minute. Okay, if I look at the, if I cut this thing with the XZ plane, in other words, cut it halfway in the middle like that, with the XY plane, halfway in the middle like this, and with the YZ plane halfway in middle like that. In other words, take 3 planes of symmetry, because think about it. If you take 1/4 of that, 1/8 of this, the 1/8 appears on the right, below, on the right, below, etc. There's 8 pieces just like that, and they all experience the same kind of a stress distribution. So if that is the case up here, right up here, 3 planes of symmetry, 1/8. But you can also take 1/4 of it. In other words, make a cut with the XZ plane and make a cut with the XY plane. Take 1/4 of that, you get this. Let me move this thing out of the way. Yeah, 2 planes of symmetry. That's how it's done in the book, by the way. And you can take a cut with the XY plane and model it as 1/2 because there's only 1 plane of symmetry. All these 3 problems, all these 4 problems can be solved, and we're going to do it today. Okay? It turns out that the hardest one is actually the one you see on the very right. It might seem to you that, oh, this is easy, I don't have to think. It turns out it can be the hardest one if you think about it. Well, first of all, are there any questions? I don't hear anything. I hope that you're hearing me, and but there are no questions. Let me,
Professor,
by the way,
does
yes.
cutting reduce the calculation time? Why do we cut it in such a way?
Yeah. Imagine that Ford Motor Company, you were working for Ford Motor Company, and Ford says, you know what, I have a part for you to analyze, and I'll give you some computer resources, and the computer resources is going to be using 1 million elements. Okay. You know that the smaller the element, in principle, the better results. So would you rather put 1 million elements in the 1/8 of the model, or 1/2 of the model, or 1/4 on the full model, if these are all giving the same answers? Which one? All you can do is use 1 million. I'm sorry, say that again.
The smallest one.
Yes, that's why we got it. Exactly. Now, of course, I have to tell you that in the old days, and when I say the old days, we're talking about, all right, 20 years ago. 20 years ago. Disk space was very expensive. I bought, at the university, I was working with a colleague, another colleague, we bought a disk, an external drive. You know what an external drive is? The one that you put in a USB right now, right? External drive, which had 2 gig of space, and we paid $3,000 US for it. Those days, it mattered a lot. These days, you bought a USB 256 gig for, I don't know, maybe 50 bucks. Okay. So, but you might, this is true. In other words, space is not very important these days. However, at some point, you will run into a hard wall. Okay, at some point, space becomes important. Maybe 1 billion element is not an issue, but when you take 10 billion elements, the computer goes to its knees. Okay. Now, so we're going to model all 3 of these. Okay, let me start with modeling of the actual block. Okay, so we are done here. Let me go to CATIA. There we are. We start with a part file. And I'm going to call this thing part, not part 1. Okay, immediately I save. File, save management, save as, desktop, new folder, This is May 11, lecture 1, lecture section 1. That's what I mean. So I have both people for 53 and 54 in this class. Okay, and in there, and should I call it part no symmetry? No symmetry. Okay, no symmetry. Okay, and okay. All right. So if I go to my folder, I see something saved there, which is called part no symmetry. Okay, let's make it. On a convenient plane, on that vertical plane, I will sketch a rectangle with centered rectangle, and you will see why I insist on putting the center of this rectangle at the origin, because later on, I'm going to come and start cutting it with the XY plane, YZ plane, XZ plane. You don't have to, if you want to cut it and you don't have a plane, you've got to go make it. That's the only hassle. That's all. Let's put some dimensions here. I think this is 10. 10. This one is 4. I'm going to put a circle there. Center. Radius is 1, according to what I'm told. Diameter 2, radius 1. Okay, exit. And pad it. Because I want to cut it at some point, I can do that with a mirror extent. Each length into the board, into the screen, and out of the screen being 1 inch, a total of 2 inches. There we are. This is my part. Save it. All I have to do is do the floppy, because I already did the file save management. Every time I do the floppy here, it overwrites the other one. Okay, good. Let's apply material to it. Steel, metal, steel on the part. Okay. And the properties of steel, these are the default properties of steel. If somebody is very finicky about these and they want to know exactly, use exactly the same properties, okay. Oh, this was aluminum. Ooh. Okay, so let's fix this thing. Cancel. Delete this. Okay, so let's do aluminum. Metal, aluminum on that part. You say okay, double click on it. Analysis. Okay, it's this number. If I want to use exactly the same value, 10.15, 10.15, that's good. And the Poisson ratio is 0.346. Oh, 0.346. I must have used these numbers. Okay, fine. Okay, good. But you can change it there in case you have something that's Poisson ratio is a little bit different, etc. Now, save it. Can somebody tell me, am I done with the model? Is there something else I have to do here?
Sir, I think you made your hole too small.
What was it supposed to be? It
You
says
made
radius 1.
diameter 1, it was radius
Oh,
1.
I did? Okay, no problem. That's great. So I go fix it. Excellent. So we go 2. How about that? Okay. Very good. Save it. So back to my question. Am I done with the part? Is there something else that I have to do? No. The part is made. That's it. Okay. So we saved it. The next step is to go to the finite element module. Now, CATIA calls it analysis and simulation, generative structural analysis, right? Static, that's what you're doing. It looks at the overall size of the object, and based on its own algorithm, it comes up with a representative element size. Okay? You can change this. You can make it bigger. You can make it smaller. But this initial size is based on the overall dimensions of the part. It doesn't think. It just says, hey, something is 10. I'm going to make the size of the element maybe 1/10 of that. So it's going to be 1 or something like this. Now, I'm not going to change this, but let's look at it a little bit in detail to see what happened here. Double click on it. The size of it is 0.1. oh, sorry, 0.625 inches. There is something called a sag. Don't worry about the sag. I will tell you later what it is. Don't worry about it right now. The type is parabolic, better than linear. Okay? So we keep it like this. But I insist on having finer mesh around the hole because you told me that the critical area is around the hole. If that is the case, you better have a good mesh there, because if you don't have a good mesh, small size elements, it will basically overlook possibly that area of critical stress values, okay? And you remember how you do this. You go to Model Manager where the traffic light is, second toolbar from the left, local mesh size, and what it does, it based on whatever I did this morning, which I used 0.1, it assumes it's 0.1, but you know what, I'm going to make this thing 0.05. And it says where do you want to refine the mesh? Well, it's this hole, not on the top, not on the side. You can if you want, but there. You see this? Right there. You see this? That's too small. So let's make it 0.1, see how it looks like. That's better. Okay, good. Now, if you want to see the mesh is there. But if you want to display it, because this morning somebody asked me, well, why do you have to see the mesh? Well, you don't have to. But if you want to see it, right-click Mesh Visualization, and okay, there we are. Okay? All right. So, okay. Now, the rest of the problem, is, you know what I was going to do? Oh, this was one no symmetry, right? Part with no symmetry. Very good. So that's okay. So let's see now. Deactivate the mesh. Deactivate the mesh. Man, I started doing the hardest one for you. That's okay. Don't worry about it. So first of all, let's save this thing. File, save management, the analysis, save as. In that same folder, I'm going to call it no symmetry. No symmetry. Okay. And okay. All right. So what we're going to do is we're going to put a force here, 2,000 pound here, 2,000 pound on the other side. This is a force that I'm putting there. So force on this side in the direction Y, 2,000. Get this thing out of the way. There we are. See that? Oh, what happened? 2,000. 2,000. That's better. You see this? 2,000. On that face, we say OK. And on this side, also 2,000, except that the sign is negative, minus 2,000. There we are. Okay. And I'm pretty sure you're happy with this, and for a good reason, obviously. You should be happy. And we're going to try to run it. And we're going to say, OK. And it will run, but it will bomb out. Notice that the reason it's taking a little bit longer than usual because we use the fine mesh, right? There it is. It says factorized matrix computation, singularity detected in translation, possible reason, missing restraints or connections, etc. So good. What does that mean? Probably means nothing to you. But the good thing about CATIA is that when something bombs out like this, it didn't run. We still can plot the deformation, and maybe it will tell us something about the mistake that we made. Deformation is this. Notice that we cannot plot the stress for a good reason, because they don't want an engineer to get to this point. It is wrong because it didn't run, but look at the stress, and that stress is garbage. So they won't let you plot the stress for a good reason, because it didn't actually run. But I can plot the deformation and plot the displacement. Displacements are rich. It's going to be 10 miles or something like that. But the deformation right there, and you can animate it. Do you see what happened here? This is moving as a rigid body. And do you see why? Imagine that you and your friend were standing in the room. Somebody was pulling this with, I don't know, 2,000 pounds. The other person was also pulling it from the other side, 2,000 pounds. There is no problem. Okay, you get displacement and everything. But imagine that both of you were sitting in the back of a truck, and the truck was moving, and you were pulling on this thing. So you don't know how much displacement each node had, because the truck is moving as a rigid body. This is in equilibrium. However, there are no restraints. That's why it's moving as a rigid body. So what is the way to fix it? Well, first of all, this is the hardest one. I told you, it's the hardest one. First of all, let's get rid of whatever we see on the screen. Deactivate it. Now, you might say, you know what? I don't know how to fix this, but one thing I know is that I can clamp that end. You can clamp that end. So let's go ahead to load. This one I delete. Instead, I'm going to clamp it. Guess what? You can run it now, and it will work fine. But we come to that in a minute. Do you have this feeling it takes longer because these are short, these are very small elements? I should not have used those two small elements. I'm going to change it later on. Good. It didn't bomb out. Does it deflect correctly? Yes. But you might say, well, nothing is moving. Why is that? That's because the last time it bombed out, the software had to adjust the scale factor, and it keeps it at that low value. So I'm going to say default. You see this? This is called amplification magnitude. Default, there we are. Okay, okay. All right. So you solved the problem, but this is not the same problem. This is not the same problem. You solve a different problem. However, you might argue that, you know what? I don't care whether you're telling me I'm pulling this thing with 2,000 pounds. The wall is acting as the other person who's pulling the wall. It's the reaction force at the wall. 2,000 to the left, on this side, 2,000 to the right. So essentially, I'm solving the same problem. And you're absolutely right. But stay away from that end. Stay away from that end, because at that end, you're not applying 2,000 pounds the way you intended it. This emulates that process. But in here, the stresses are quite good. It's going to be quite good. This process is this thing is called Saint Venant principle. In other words, if you stay away from the source of disturbance, the source of disturbance, basically, things are going to look the same. For example, I don't know, how do you say this thing? Well, you get the picture. All right, now let's look at the displacement. This is the deformation. It's not numbers, okay? Displacement is right here. Let's change it to average ISO. There we are. This end is clamped. It is fixed. This end is moving. Biggest displacement is on the right. And you can see that that's reasonable. These are small stresses. Well, but you know, this is not gum either. This is a piece of steel, aluminum 2 inches by 4 inches by 10 inches. So it's not gum. Okay? It's not going to stretch like crazy. But look at the von Mises stress. And just like what you told me, look, top and the bottom have the biggest stresses, von Mises stresses. This number is the stress on the top and the bottom is actually, even if you look at the stress, in fact, the biggest stresses are not there. The biggest stresses are here, total garbage, or at least corner locations. Look at the way it deformed, okay? Now, if you want to look at the stresses here, I'll show you later on. You create a group and show it. I'll show you later on. But that's not the issue right now. The issue is something else. So how do I solve this thing? I don't want to see it like this. Okay, so let me go ahead back to that clamp and delete it. First of all, let me deactivate this fellow. You go to the strain, delete the clamp, okay? And put the load there, the 2000 on this side. Very good. Now, if I run, it's going to bomb out. You know that. So I'm going to take away the rigid body motion. There is a quick and dirty way of doing it. And if you, I'm not going to tell you what it is, but if you're that curious, look in the channel and you'll find it. I am not going to say that for a good reason, because people use that recklessly without thinking, and it's going to be wrong. So if you abuse that, it's going to be wrong. I'm not going to say it. Here's the way I'm going to fix this issue. But first of all, I don't want this thing to fly away. Like I don't want it to be in the back of a truck, basically, and the truck moving. So I'm going to say this point, I want 3 displacement being fixed. One way, of course, is to clamp it. Okay, one way is to clamp it. Clamping means that point is fixed. But I'm not going to clamp it. I'm going to use this other icon here, which says enforced displacement, enforced user-defined displacement. Okay. All right. So I'm going to take that corner point, and solid elements have only 3 degrees of freedom. So that corner point does not move in direction X, Y, and Z. These things are irrelevant. You can check it, uncheck it. It doesn't matter. For solid elements, it's irrelevant. Okay, but don't check it. So that point is not going to fly away. It still can hinge about that point. It can spin about that point. So fine. Another point, say that point. I'm going to say, you know what? I don't want this thing to spin and rotate about the axis X. So I'm going to say you cannot move in the direction Z. Z is 3. And you cannot move in the direction Y. You can move in the direction X because this thing shrinks to the Poisson ratio effect. But this will ultimately, if left like that, it can hinge about that edge. Think about it. Now, to prevent making it hinge about that edge, I'm going to take another point and say, don't go up or down. So don't go in the Z direction. When you think about it, this is called the 1, 2, 3 rule. 1, 2, 3 rule. There is a quick and dirty way of fixing this thing in CATIA. And if you can figure it out, by all means, use it. I don't care. But I'm not going to tell you unless you go and figure it out in the channels, in some video in the channel, and come and discuss it with me. Okay, let's run it. Man, I should have changed the size of that element. This is why on the test, we ask you to do default element size, unless we ask you to refine it. And even if you ask you to do that, don't go crazy, like what I have done here. Done. Didn't bomb out. Deformation. There we are. Animation. Exactly like you that point, but you didn't clamp it. Stress. Same type of animal. But once again, notice that these ends bulge out. Bulge out. Okay? Now, if I don't want these things to bulge out, okay, what I can do instead of a stress here, instead of a force, I can apply pressure. Let me show you what happens when you apply pressure. So I'm going to delete this and delete the distributed load. And we go apply pressure here. Pressure right there, pressure. On that face, now this we have to do it ourselves. 2,000 pounds divided by this area. This area was 4 by 8. No, 4 by 2 is 8. 2,000 divided by 8 is 250, right? 250, and it's tensile. So you put a minus sign here because 250 positive is going to compress that face. See this? It may look the same, but it's not the same. And the same pressure on this side. Believe me, this is not going to bomb out, okay? But that's not the issue. I wanted to show you what happens at the ends. Is there a bulging? Done? Here is the, here's the deformation. And let me plot this. Look, there is no bulging here. Okay? Well, first of all, the moral of the story is that if you can avoid distributed load for real problem when they pay you for something, avoid it, because it may cause for solid elements, it may cause hot spots, and those hot spots are not physically possible, because there is no such a thing as a concentrated force or an edge force or a phase force. There's pressure, and that's different from the way that thing is operating. Is there a question? Do you have a question? No? Okay. I told you that this seemed that it was the easiest way of doing the problem, but because of this 1, 2, 3 rule, we had some issues and we had to fix it. Now, I'm going to save this because I want to repeat this problem with 3 planes of symmetry. Okay? So let's go ahead. I'm going to kill this. And this part, I'm going to save it as File, Save Management. This, I'm going to save it as 3 planes of symmetry. This was no plane of symmetry, 3 planes. 3 planes. Say okay. Say okay. And now go to generative structure analysis. Oh, I have to cut it, right? I have to eliminate 3. Let me basically cut this thing with 3 planes. So here's a split. A split this way. A split that way. And split this way. This is 1/8 of that part. Save it. And now go to generative structure analysis. Let's do some local mesh definement here. I like it. So here, but I'm not going to use the same number. This was too small. So we make it I don't know, 0.3 maybe. Yeah, it's more respectable. It's still smaller than that. Okay. And you look at your mesh. That actually doesn't show that much. How about 0.05? What did I do here? 0.05. 0.05. Let's see. Oh my God, this is even worse. How about 0.1? That's still small. 0.2. Okay, that's fine. I just wanted to show you, to show you that it is smaller there. That's really what I wanted to do. Okay, good. Deactivate. Now, this was, if we were applying force here, 2,000 pounds, don't use 2,000 pounds, divide it by 4, right? because the 2,000 pound was applied on this big rectangle here, which we cut it into 1/4 of it. So if you apply force, do 500 pounds. But if you're applying pressure, let's go ahead and do the pressure on that face, minus 250, pressure does not change. Okay. All right. Pressure on that face, minus 250, and lose 3 marks out of 10. Why is that?
You forgot the rollers.
Yeah, this is not where the pressure applied. The pressure was applied at the other end that we didn't model. It's not the pressure. This is wrong. Don't apply any pressure here. Okay, it's a surface slider. There. And I can do this thing 3 times separately, or I can do it all at the same time. These are all planes of symmetry. Say okay. It's very common that people get really carried away and they also apply surface slider here, which is not a plane of symmetry. Okay, so let's run it. Don't worry about that. Deflection. There we are. This is the way it's supposed to be, isn't it? This is supposed to cave in. Huh? And stress, 1 meter stress. Biggest stress on over here. Notice that when I apply the load, the red dots, the biggest red dots were out here because these were unrealistic. But when you apply pressure, it got rid of that and it shows you the critical area the way it's supposed to be. Okay? All right. So save this, file, save management, your analysis, save as. This was 1 plane of symmetry, right? 1 symmetry, oh, 3 planes of symmetry. Sorry, 3 planes of symmetry. Very good. Let me say okay. And we are done with this, so we're going to close it. Now we're going to do it with 2 planes of symmetry. That's the way it's done in the book, okay? The way it's done in the book is I didn't cut it in the middle like this. So one way to fix this is to go here to split this split, right? This split. No. Yeah, this one. Either delete it or deactivate it. It's up to you. There. The advantage of deactivating is if you change your mind, you can come back and do it. You don't have to go there, click it. Or you delete it if you want. I don't care. So file, save management. Oops, wait a minute. File, save management, save as. This time we're going to say 2 planes of symmetry. 2 planes symmetry, as done in the book. You say okay. Now we go to generative structure analysis. Say okay. Let me do the refinement here for you. Okay. Unless you're asked to refine, don't refine. See that? Finder there. Deactivate the mesh. I deleted it. That's okay, no problem. Okay, so surface slider over here and at the bottom, not on the sides, because last time I cut it also there in the surface slider. Pressure at the end. Say okay. Save the analysis. Save management. Here's the analysis. Save as. This was 2 planes, right? Yeah, 2 planes. Actually, let me do this. 2 planes of symmetry. This is because I want to keep all of them. I don't want to overwrite the other ones. Okay, run it. And guess what's going to happen? You'll see. Don't worry about that. It will bomb out. And maybe if you plot it, the displacement, it will tell you something what's wrong. Look, this is free to move as a rigid body. It's on roller on the side, it's on roller on the bottom, but nothing's stopping it from moving in the X direction. When you took 3 planes of symmetry, that surface slider prevented the movement in that direction. So we say, fine, we got to fix it. We got to fix it. So deactivate this. By the way, when you see an exclamation mark here, means that something happened, didn't run. So just brings your attention to it. Deactivate. So I'm going to take 1 point and say, hey, you cannot go to the left or you cannot go to the right. Okay, that takes away the rigid body motion. And how do we do that? We go to user-defined strain right there. See, this is the clamp. This is surface side. There isn't much of other things here, but don't worry about it. Okay, so this is user-defined strain. You select 1 point. It doesn't matter. You take this or that corner or that corner. It makes no difference. Do not move in the direction X. Do not move in the direction X, because that's what it was doing as a rigid body motion. Let's save it. And this time it will run. Okay, deformation, what I expect. Now, why am I not seeing anything? Why is it not magnifying? Why is it not animating it? You should know the answer now. Help, help. If it ran, why is it not?
Scale was determined
The
in the previous
scale,
solution.
yes. That's right, because last time that I ran, the computer went crazy, CATIA went crazy, said, you're giving me 1 mile displacement, so I'm going to scale it down to 1,000 million times smaller. It's going to keep it like that unless you change that scale by going to default or putting it yourself. Default, see that? There we are. And now you can animate it. And you can look at the stress, no problem. Save this. Okay. Now I'm going to do it with 1 plane of symmetry. Okay, so get rid of this. Back here. Let's kill this guy. Deactivate it. There we are. Save this thing. File. Save management. Save as. 1 plane of symmetry. 1 plane of symmetry. Say OK. Say OK. And then we're going to go to generative structure analysis. But once again, if you want to refine it, fine, let's go refine it. Same number. Okay. If you want to look at the mesh, believe me, there's going to be a finite mesh in the hole. You can see that. All right, deactivate this. All right. So what do we got? What do we got here? We have surface slider at the bottom and on this side, right? We've got pressure on this side and of course on that side. And run it, and it's going to bomb out. And you can see why. Because this is like being on roller, right? It can go everywhere. It can move in the XY plane. It's still, be in equilibrium. So I'm going to take away the rigid body motion. See that? You can check it out right there. You can see it. It's like a fridge sitting on the wheels underneath it. Okay. Now, to fix this, first of all, deactivate this guy. Okay, so it is moving as a rigid body. So what I'm going to do, I'm going to take 1 point, for example, this bottom point. It cannot go up and down. We know that because of the surface side there. But I'm going to say, don't even move in the X and Y direction. Can you see that this is not good enough? Because it's hinged about that point. As if somebody grabbed the corner of the fridge on that point, Somebody else can still push it in the XY plane. It's going to spin about that point. So we need one more point so that it does not move in the direction X. This can no longer spin, okay? Or you could have taken that point, or you could have taken that point. It really doesn't matter. Sometimes I make mistakes too. Right. Change the scale, amplification. Oops, default, that's what I meant. Default, there we are. And yeah, so animated. Let me plot the von Mises stress here for you. I want to show you that over there, nice and flat, no hot spots because you applied pressure. Nice and flat, no hot spots. The last thing that I want to do today is to show you the difference between, again, pressure and force. Where's my other pressure on this side? Did I not apply two pressures? Yeah. Oh yeah, it went in. So okay, it went in. It went in. You can't see it. By the way, before we go there, double click on this. If it says don't show me the deformed shape, there we are. You can see your pressure here. You see that because it moved and it kind of ate those pressures. Okay, so let me deactivate this. Go and take these pressures away and apply the force. Delete. Delete. Force on this side. 2000 minus 2000. Force on this side minus 2000. Oh, this first one should have been plus 2000. What do you think is going to happen to you if you gave us this? I'm trying to help you. You run this thing. It will run. But you expect full marks.
Would the corners bulge?
That's not okay. I said that. That's okay. You can do that. They will bulge. You're right. You're absolutely right. But there's something else that I've done here that's wrong. The corners will bulge. That was the purpose of doing this. I wanted to show you that it will bulge. But there's something that I've done that makes you lose 2 points out of 10. The force. It is not 2000 anymore. It's 1000. Because the 2000 was applied on the entire back side of this, which was double this area. So this is wrong. This should be 1. And this should be 1. Now we're going to run. No problem. It will run. There will be bulges there in the corner. That did run. Let's make sure that, yeah, right there. Look. Let me show you the deformation right there. You see this? You see this? These are unrealistic. Now, the reason that when I plotted the strain, it didn't bulge is because I insisted fix this so that it didn't show the deformed shape. Right there. Right there. You see that? The biggest stress shows on these corner points, which are totally fictitious. It's because of the boundary condition. It overwhelms the red stuff here. The red stuff should be there. Okay? Now, this is fine. Give me 2 minutes and I'll let you go. Or 1 minute, actually. I want to see my stress here because I know that these red stuff are killing it and they're totally useless. So what you do in a situation like this, let me deactivate that. Deactivate it. You create a group. A group, if you have access to the book or you're watching my videos, I use a lot of groups right there. There are different ways of making the group. So let me make a box group. Where is it, by the way? Did it make? Oh, it's right there. Gee. I move it here. And I can resize it and say, hey, just show me the stuff in that box. So you created the group. This is a box group. Double click on 1 meter stress. On this selection, don't show me everything, just show me the box. And hide that. There's your red stuff. You couldn't see it before because these unrealistic stresses at the ends were masking that. The purpose of a group is you select where you want to watch your results. And under St. Venin principle is that it says, hey, stay away from those two ends because you don't know what's happening at those two ends. You put pressure, you put load, so that's ambiguous. Okay, stay away from that. Show me where it's important, top and the bottom of the guy. All right, that's exactly 450. Oh, I like it. Okay. So as far as I'm concerned, I'm done. Are there any questions? Let me stop the recording here, okay? And then I'll entertain any questions that you might have. By the way, let me save this. Analysis. File, save management, analysis, save as, one plane of symmetry, right? One plane of symmetry. Now we have everything. I can come back tomorrow and look at them if I didn't destroy anything. Okay, so let me stop this.